And then last up in the session today, we have Evan Durnall from MRI Global talking about efficacy determinations of commercial decontamination products for clandestine laboratory and bulk remediation. So Evan is a chemist and program manager for MRI Global with over 18 years of experience in test and evaluation of commercial off-the-shelf and emerging chemical detection and decontamination products. He's well-versed in development and validation of chemical collection devices and Siburney-related detection and decontamination products. In addition to holding multiple hazardous chemical handling and response certifications, he has experience in chemical agent handling, as well as synthesis, detection, and decontamination of fentanyl. So take it away.
Thank you very much. Appreciate it. I will do my best to recognize the fact that I'm now the only person standing between you and lunchtime. So I promise you will be extremely surprised at how quickly 97 slides can go by. We've got this down. Just a quick bit, since I do not work for the EPA of MRI Global, who we are. We're a not-for-profit research institute headquartered in Kansas City, Missouri. Got about 400 employees. Of all the stuff on this slide, the thing I'm most excited about is that we're getting ready to enter our 80th year of independent research and development for a broad variety of customers. It made me kind of take pause this morning in hearing Phyllis brought up. I started my career at MRI Global as an intern on a Phyllis program as a set of hands in a hood almost 20 years ago now. So it's kind of fun to hear that continue to go and go through there. Our expertise, if you will, spans 4 different business units across the spectrum of physical sciences, life sciences, and engineering. But you're not here to hear me talk about MRI Global, so we'll really get to the point here. I'm here to talk about kind of this impetus for a standard of efficacy and things like that. Don't adjust your glasses. Don't pull out your contacts. It's foggy, right? What does effective degradation, destruction, and neutralization really mean? Is there a great definition for that? We had a couple other, or Amy, you started out this morning talking about, we need to define things really well, especially as scientists. This is kind of this efficacy. What does it really mean? What does it really look like? Efficacy statements are not created equal. They all are certainly, founded in good science, but they have different places for different statements. They can often lead to overstatements, misunderstanding, misinterpretation for those not familiar with the techniques, for those end users that are less familiar with the chemistry processes, those types of things. A big part of this is that publicly available data for opioid and clandestine lab remediation they're definitely improving and out there, thanks in big part to a lot of folks doing research at the EPA, but they're lacking. And again, that kind of ambiguity of terms, right? What does efficacy really mean? What do we mean when we say degradation, destruction, neutralization? I'm not going to say removal a whole lot today because that's kind of a different beast when it comes to decontamination, right? Physically removing something is significantly different oftentimes than neutralization of a threat. So what other considerations? That's a different one. Considerations here. There's a dad joke in here about having bitten off more than I can chew with all these 8 terms, but I'll leave that to you on here. But it's really things like what phase of development is a product in when we're going to do an efficacy study? Is it a brand new formulation? Is it something that's been around for a long time? We're trying to compare it to a new threat or evaluate efficacy to a new threat. What type of test material is available? Are we talking about solids, liquids? Are we going to do this on aerosols? Some combination of the two? What type of test material is applicable, right? What's your target operational scenario? Is that going to be bulk remediation? So, maybe removal and then bulk remediation of a large volume or mass of products? Is it, a site cleanup remediation of a clandestine meth lab, but there's nothing expected except for slight or trace residual residues on surfaces, things like that. So all these things are really, really important when you're starting to talk about what efficacy really means when you're evaluating and developing these products. So you can't have a chemistry presentation without some structures on board. So these are some of the most commonly studied ones, obviously methamphetamine, fentanyl, and carfentanil being popular, if you'll allow the term popular for that. There's kind of this 3-stage approach when we're going to do these. If it's a developmental product, you're going to start to develop that formulation and go through those initial proof of concept type studies, right? It's going to be based on some stoichiometry. Do I have enough, or what's my limiting reagent in here? Do I have enough active ingredient, if you will, to adequately destroy X mass of a threat material? These are probably going to be done in kind of stirred reactors, very simplistic setups, typically going to be measured with something as simple as colorimetric. If the decontaminant doesn't mess with the colorimetric chemistry, NMR can be used for this as well, because it can give you that kind of good near real-time or real-time information also. I'm going to move then from proof of concept and formulation development to quantitative testing. Within quantitative testing, obviously, there's a lot more than method development and validation to be done at that point. I'll talk a little bit more about that in a few slides here. You're talking now stirred reactors. Maybe you're looking at some surfaces, porous versus non-porous, those types of aspects. Going to typically be done more now with the chromatographic method and maybe some mass spec. Not to say you can't do quantitative measurements via NMR. It's just typically more sensitive with chromatography to be able to separate out all those interferences and byproducts that can be introduced by a decontaminant in the effluent stream. And then you got to start getting into the operational testing, right? Stirred reactors, surfaces, aerosols, very quantitative methods, right? What threat forms are you targeting? Targeting bulk, solid? Is it a liquid threat? What are the application methods? Am I pouring this on? Am I spraying this on? Am I ionizing this in some way to create a fine, mist to enhance surface areas? What are the application ratios? I don't think any responder or end user wants to carry a 55-gallon drum of liquid decontaminant with them to be able to decontaminate a gram of fentanyl. It's just not operationally relevant, right? Well, the contact times depends on that operation as well, right? If you're doing site remediation, you want to make sure things done. Maybe an hour or 2 hours or 3 hours of contact time isn't a big deal. If it's an emergency situation where something has to be, degraded as quickly as possible, maybe you need that in 5, 15, however many minutes. Flip side, is it, residential situation or a hospital situation, more kind of the typical FDA, EPA type of surface cleaning, contact times of 1, 5, 10, 15 minutes are more available to or more realistic to expect. So within this formulation approach, you go kind of what that theoretical need is. Like I talked about, you can evaluate singular mechanisms at a time. You can look at multiple mechanisms at a time. You may or may not be surprised that there's not an abundance of stoichiometry cartoons available on the internet. So this is about as close as I could get. So if you're a cartoonist and you know stoichiometry, there's a market there for you. And you go through these iterations, right? Won't get into it, right? But you're basically just looking at the structure, the molecular formula, the structure of the compound, converting that into moles, and then looking at how that actual threat is going to be reacting with the one or multiple active ingredients, if you will, in your decontamination product. From there, you're going to also consider, what is this test material? What are we going to start with? There's all kinds of different permutations of this, right? DEA has done a good job of getting us these fentanyl profiles and similar profiles for other clandestine materials, right? Powders found, I think in the US, I think this was calendar 21, averaged about 14%. Sorry, that unit is cut off there. So that's about a 14% purity on average of powders found. Pills are right around that 2 milligram, which is a little scary because that's also right around the typical lethal dose of fentanyl. And then you got lab grade materials, 90, 95 plus, 99% plus pure material. What's the best to start with? One's more operational, but one's going to be worst case. You don't want to have done all of your tests on a 14% pure material saying I've got 100% destruction. And then you go to something that's now 50% pure and your destruction isn't nearly as adequate. The different salts. HCl is the most prevalent fentanyl salt out there, followed by citrate. I wouldn't say followed closely by citrate, but it's followed by citrate for most. That's similar to amphetamines as well. So usually going to end up dealing with the HCl or citrate salt. That typically doesn't have an effect, especially when you're talking about liquid or aqueous-based decontaminants, because that salt's just going to dissociate once it goes into solution anyway. So you're really just looking at the actual active material itself. again, making sure you start with the right material, whether it's lab grade or street grade, can be really crucial. So we get into this proof of concept and qualitative testing. You see each different technique kind of has its different approach. The right-hand column there on the side is approximate LOD. Don't put me on a stake for those LODs being rough approximations for everything. Obviously, different methods can vary depending on the detection limit. But generally speaking, colorimetrics are going to range at best in that 400 to 500 nanogram range, up to 20 plus micrograms. I'm kind of stricken through iron Raman on here. A lot of times people ask, why can't I just do iron Raman? The sensitivity is just really not there when you're going to do those types of optical techniques for those. You're looking at 5 to 10% at best, and you're probably going to have to do some manual interpretation. So they're really not overly applicable when you get to that point. NMR is another good one that's frequently used, as well as GCMS and LCMS. Certainly caveat being that in theory, you can run an NMR for ad infinitum and your detection limit keeps going down, but the reality and costs of running an NMR for days and days and days isn't really practical. So you're going to look at this type of testing and just say, we're going to contaminate via liquid spike likely because that's going to be the easiest, quickest, lots more replicas to do. And I'm going to really evaluate kind of the presence or absence of fentanyl based on what my detection method is. Or maybe I'm looking at a change. NMR is going to be able to show, hey, I had fentanyl, I've applied my decon. Now I've got a little bit of a change. It's not necessarily going to give you that percentage depending on how your experiment setup is, but that's really kind of the purpose of that level of testing. We'll get into the quantitative aspects here. Obviously, everybody's pretty familiar with the difference between qualitative and quantitative aspects. Very similar things. You're going to look at how you contaminate. Maybe now you start to look at powder versus liquid contaminates or bulk, if you will, powders versus very, very low level residue type powders. And then you're going to evaluate your method. You need to know the method detection limit, right? We talk about all these kind of clean standards. If I say clean, what does that mean? In the chem agent world, which I'm also familiar with, there's GPL and all those types of things to say it's clean to X level, right? You can't ever truly say clean to 0 based on your measurement technique, right? You have to be able to prove 0 before you can get down there. So you really want to know what that method detection limit is based on the instrumentation that you're doing. And quenching is really important in these types of tests also, right? Especially if you're doing operational tests further down the road, where you're saying if you apply it for 10 minutes or 15 minutes or 30 minutes, what's that do? You want to be able to really kind of tighten up the precision and accuracy of your study, just so that outside of doing a real-time analysis technique, that my reaction had been quenched before I did my sample analysis, because samples may sit in an instrument for 2, 3, 4, 5, 6 hours. You want to know that that sample was the same when you put it on the instrument as when you take it off the instrument several hours later. So that's the importance of those quenching techniques as well. Here's kind of example of some recent work we've done. I will say some of the data you'll see throughout here is based on a variety of products that we've tested. It's not all from one single product. So it's kind of a smattering here. Just to show the differences between the liquid threat form of a material, which is shown as the blue dots, and the solid threat form. One of the biggest things about this, and why we suggest using a liquid spike earlier on in your studies, is that you can get much tighter precision and accuracy with a liquid spike. You're not going to be dependent on the solubility of your threat material and the decontamination material, which can often be highly dependent on pH, which we'll get back to in a minute too. So it kind of shows that, the error bars, I didn't forget to put error bars on my 30 and 60 minute liquid spikes. They're that tight. They really are. A combination of the duration of the time, but also just the fact that the liquid spike allows you to be much more precise in your reproducibility on there. So there's a couple different examples of that in here. We talked already a little bit about analytical methods. My hit colorimetric, my fentanyl LCMS parameters are cut off there, but it's not important. But we're typically talking about proton NMR, right, or carbon-13 NMR, and then frequently with fentanyl or other opioids, you're looking at LCMS, MS, maybe GC if you're trying to do some effluent analysis to try to still get some identifications of those products. But there's a broad variety of analytical methods available, right? There's not a shortage of ways in a lab to detect meth, fentanyl, carfentanil, xylazine, whatever that may end up being. too fast. Definitely don't want to fly through quality assurance. So I've got multiple slides on QA, and that, there's a reason for that, right? For the scientists in the room, if you don't have QA, if you don't have QC, you really don't have anything, right? So really putting in an emphasis on, what that quality control should look like, what, potentially you as end users or folks looking to find a product, when you get that report, what does my report look like? What is the quality level of that report? What are the different negative controls, solvent blanks, instrument blanks, matrix blanks? We can add different types of controls and blanks out the wazoo here. Similarly with our positive controls, right? For the quantitative aspects, obviously you're going to have a calibration curve of some kind, depending on multi-points and fits and all those kinds of things. You're going to have to maintain and demonstrate the sensitivity and specificity of that method. You're going to demonstrate the recoveries, and this is where we get into that method development, validation, quench samples, all of those types of aspects. Any good report or test plan should have a data quality objective table, right? I've taken out some percentages in this one because they can vary lab to lab, and depending on what your ultimate goal is, they can vary pretty significantly. But it's always good to consider those when reading a report or looking at a report as to what those objectives were. There's certainly a place for a broad or less strenuous objectives, but there's also definitely a place for that more rigorous objectives out there. All right, so now let's get into the fun tests, the operational tests, right? We've done the calculations, we've contaminated, we've done liquid spikes, we've done a few different tests. Now we're going to really start to look at how can I use this product in the field and verify that it's going to work in the field. Unless you guys hit the lotto or know of somebody that's got deep pockets doing real field tests at scale with opioids and methamphetamines and those types of things is very, very cost expensive, right? Let alone the challenges if you can even be permitted to release, if you will, something in the environment, which is going to be a no. Spoiler alert. And so you really have to do these at a lab scale, but you really want to make them applicable, right? I think Dr. Magnuson and some other folks that are here summed it up best a few years ago in a similar presentation, talking about, bench scale, but realistic scenarios. What can we do in a laboratory setting to really make things as applicable as possible for the end users? We can evaluate things, like I said, application time, application ratios, contact time, solubility. We hit on that. Most aqueous-based products, depending on the pH, that solubility, especially with fentanyl and other opioids, is going to really, really vary. So you have to pay close attention to that as you go through these types of settings. Fortunately, there are lots of good methods in terms of wipe sampling, like the one shown here, based on NIOSH and ASTM methods that are shown that you can do with surfaces, whether you're going to extract the surface, extract the wipe, analyze the effluent. These sample matrices and test matrices can get really large really quickly if you're not careful. Let's see here. Some other operational examples going through, different application methods. The charts here just demonstrate the difference between just kind of generally pouring, if you will, a decontaminant on a product versus spraying it on a product with a kind of a commercial gross sprayer. Gross being it's not, atomizing or anything like that. But you can see, or is there a difference? Does it matter if my customers, pour it on or spray it on or figure out some other weird way to apply decon? And also it's a little bit cut off, but you can see the carfentanil side. What does that mean, right? What is that clearance threshold? Most people accept that kind of range for methamphetamine that's been around for a while. The EPA a couple of years ago put out some good voluntary guidelines. I think the key word on there is that there's still voluntary guidelines, as far as I know. Please correct me if I'm wrong. Of methamphetamine and fentanyl and other opioid laboratories, but there's really not that set. It has to be this level out there, and that's pretty important. But in doing those tests, you can extrapolate. That may be a dirty word to some folks, but you can kind of extrapolate, say, if I've got this mass, what does that look like in a field scenario? If I do have residue, or if I do have a gram of fentanyl sitting in front of me, how do I get rid of that? How do I know that by putting, X mils or X liters of product on here, it's actually going to take care of this? Some additional work that we've done just very recently with contact time, application ratio. You kind of already saw the solid versus liquid type stuff. Those error bars tend to decrease over time also. That's predominantly or likely associated with the solubility of the material. As you're more and more certain it's becoming soluble in your example, you can see that you can start to generate curves like this. Similar to this, so this is kind of a amalgamation, if you will, of all the independent data points from that solid liquid chart, as well as the time. So you can start to see the good news here is for those folks saying, I want to do an initial proof of concept study with a liquid spike, but my operational use is going to be a solid powder. How do I start to correlate? Does that do me any good to do a liquid spike when I'm going to go after a solid powder? You can start to see in those first couple columns as the blue and orange dots, if you will, start to overlap, that in terms of efficacy and percent destruction, so true destruction of the molecule, those start to overlap pretty well. Sure, your error and standard deviations are going to be wider, likely with that shorter times with the solid powder, but that average is going to tend to be similar to what you would see with a liquid spike, versus a liquid spike is going to give you that more precise data on there. Let's see. So now it's a little more clear, hopefully, what an effective degradation, destruction, neutralization test report will mean. It really still does need kind of that formal definition. What do we mean when we say a product is proven? We really kind of need an industry standard, like an ASTM method, things like that have been developed out there. I think all test reports should definitely be caveated. Is it a qualitative report? Is it a quantitative report? Is it somewhere in between? There's definitely a place for all of those things, and all of them serve a very good purpose in there, but it's important for an end user to kind of understand what that report really means and what conclusions they can draw from that report. And is it an operationally relevant report versus, yep, we're trying a new formulation, we're developing it, and we're going to go through and do this. And if it is an operational relevant report, some kind of operational language, and you don't have to read it all down there, of, hey, we've done this, we've done it quantitatively. Here's how it would apply in the real world based on an actual health or a health-based, remediation type level. That's all I've got. I promised I wouldn't be holding you between lunch. I think I'm right on time. So thank you. Certainly welcome to any questions or comments.
Yep. And while Paul's getting up, sorry, I realized there was a whole nother half of your bio on the next page. Just trust me, he's super highly educated, lots of awards.
No.
Yeah, I missed that. My apologies.
Dr. Gwynn said this morning, whoever writes those does a good job, and you can make a little sound like a lot. So
Paul, go ahead.
Yeah, I was wondering if you're doing anything looking at xylazine, which seems to be a common co-contaminant in a lot of these fentanyl situations, but it's not an opioid, so its chemistry might be significantly different.
absolutely. So none of the data on here was from xylazine, but definitely within the last year, we started doing more studies that do include xylazine, as it has become a more commonly encountered adulterant, if you will, for those. Yeah. And the same exact processes apply for the most part. And again, this is pretty high level generalization. Oxidation of some kind is going to be your friend in a lot of these instances. So whether it's xylazine, meth, fentanyl, carfentanyl, those kinds of things, you're going to start to look, at what active ingredients are going to provide that type of action. Obviously, there's hydrolysis, and there's lots of them. Don't quote me that oxidation is the only thing. So, but yeah, you're absolutely right. That's a good point.
Sorry if I missed it, but the graphs that you were showing with efficacy, what was the decontaminant that you were evaluating?
Those were multiple different products. Some of that has been different Decon Force products, so DF 100, 200. Some of it's been Dahlgren Decon, so a broad variety of products.
Anyone else? Everybody getting hungry? All right. Well, thanks, Evan.
Thank you very much.